So yesterday we were dealing with VSEPR theory. In VSEPR theory, to know the shapes, we classify the compounds into two categories. One is molecules with lone pairs on central atom and molecules with no lone pairs on central atom. So let's see first the molecules with no lone pairs on central atom. Example, yesterday we saw BeCl2. BeCl2, two electrons in the valence shell of beryllium and one from each chlorine. So altogether 4 electrons. That means 2 pairs. 2 pairs will be standing around this beryllium in a linear way with maximum repulsion. Means to minimize the repulsion, they stay far apart. So BeCl. So the shape is linear. Shape is linear. So 4 electrons, 2 pairs. Shape is linear. The next one in this category, that is molecules with no lone pairs on central atom, that is BCl3 or BF3 or BF3. Okay, BCl3 boron with 3 electrons on the valence shell and 1 plus 1 plus 1. So 6 electrons. 6 electrons means 3 pairs. 3 pairs. 3 pairs will be standing around boron in what way? In trigonal planar way with bond angle. What is the bond angle? 120, 120, 120, 120. Next example for you, that is CH4. CH4. CH4 is tetrahedral shape. So coming to the valence electrons, carbon CH4 valence electrons, that is 4 plus 1 plus 1 plus 1 plus 1. So 8 electrons. 8 electrons means 4 pairs, 4 pairs, and you see 4 bonds are there. So these 4 bonds in what way they are arranged around carbon. To minimize the repulsion, they stay far apart. So this is the shape of this CH4. 4 pairs of electrons are pointing towards the corners of a regular tetrahedron. Tetrahedron means you have to join them. You have to join them, join them, join them, join them, join them. So you can join them with the dotted lines, So 4 pairs of electrons. This is the tetrahedral shape. All bond angles are equal. All bond angles are equal, which is equal to 109 degree 28 pairs. So I will write this. This is tetrahedral structure. Just this is tetrahedral structure. All bond angles are equal. All bond angles are equal, which is equal to 109 degree 20 minutes. So this is a regular tetrahedron. We show it like this: C H H H H CH4 regular tetrahedron. You can join them with dotted lines. Right? This is CH4 with bond angle 109 degree 20 degrees. This is the tetrahedral angle. Maximum they can stay far apart using this bond angle 109 degree 20. This is regular tetrahedral. Next, PCl5, yeah, PF5, phosphorus, with 5 electrons in the valence shell, 1, 1, 1, 1, 1. So altogether 10 electrons. 10 electrons means 5 pairs. 5 pairs. These 5 pairs will be arranged in a trigonal bipyramidal way. Means 3 in one plane, 3 in one plane, and 1 above and 1 below. 1 above, 1 below. Like this. So here, two types of bond angles you see, that is 120 degree and 90 degree. For 90 degree, you can see up and this equatorial position. But for 120, this is, we say equatorial position. Equatorial position bond angle is 120 and this is 90. So, this is trigonal bipyramidal way. Phosphorus, Cl, Cl, Cl. I can make dotted lines to join them, and one up, that is Cl, and one down, that is C. I can join them with dotted lines. This is TBP, TBP, trigonal bipyramid, one pyramid up, like this, one pyramid up, and one pyramid down. This is trigonal bipyramidal way, that is PCI5. Next example without any load bearer is SF6, sulfur. 6 electrons in the outermost shell, plus 1, plus 1. So altogether 12 electrons. 12 electrons means 6 pairs. 6 pairs are arranged in what way? In a octahedral way. So octahedral way will be showing S, F, 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 and 1 up, and 1 down. You join the top F to this. So this is octahedral. Octahedral. Now molecules with lone pairs on the center atom. For molecules with the lone pairs on the center atom, first one is ozone. Ozone. This is hydrogen. And on ozone, there is a lone pair. Due to that lone pair, see here is a lone pair. On S, there is no lone pair, only bone pairs are there. In oxygen, this lone pair will repel this bone pair, this lone pair will repel this bone pair. That's why there is a bond angle. You can show that lone pair on oxygen. Similar is the case with SO2. You can replace that O by S. Again, on this, a lone pair is it. There is lone pair bone pair repulsion. This side, lone pair bone pair repulsion, lone pair bone pair repulsion. So you see that bond angle. Another example for molecules with a lone pair on central atom, that is NH3. NH3. In NH3, nitrogen is the central atom. See, five atoms, valence electrons, and 1 plus 1 plus 1, that is 8. 8 electrons means 4 pairs. 4 pairs will be standing around this nitrogen. This is nitrogen. This way. This is the lone pair. You can see like this. So here there is a lone pair. That lone pair will be repelling this bone pair. Lone pair bone pair repulsion. Lone pair bone. So this bond angle shrinks. In the case of CH4, there was a bond. So the shape is considered including that bond also. Now there is no bond, only covalent bonds are directional. Instead, there is a pair of electrons. Now for the shape, you see down only. So this is pyramidal structure, and there is lone pair bone pair repulsion. So due to this repulsion, these three will be coming closer. So bond angle shrinks from that 109 degree 28 minutes to 107 degree. So here only one lone pair. The next structure is, so this is pyramidal structure. Next example is water with two lone pairs. So with the two lone pairs like this, so there is lone pair repulsion, lone pair bone pair repulsion, and bone pair repulsion. And we know that So what happens here? Bond angle again shrinks. So in water, with one lone pair, it was 107. With the two lone pairs, it is 104.5. So in water, the bond angle again shrinks. The shape is V shape. So ammonia was pyramidal, water is of bend shape. Next example for molecule with lone pairs on central atom is S7. S6 plus 1, 10 electrons. And here is the lone pair. For lone pair, if you keep on this position, these positions are called equatorial position. These positions are called equatorial position. While these two positions are called axial position. These two positions are called axial position. So, if you keep on equatorial position, the repulsions only two repulsions, that is 90 repulsions. 120 is not a repulsion. 120 is not a repulsion, but 90 angle 1 is a repulsion. So if you keep this on equatorial position, you have only two repulsions. Suppose if you keep this on axial position, then there will be three repulsions. This repulsion, and this repulsion. Three repulsions. So to minimize that repulsion, we have to keep for the electron pair, lone pair is on the equatorial position. So this is the shape. The shape means this is similar to seesaw. The shape is called seesaw. Seesaw is like this. S, F, 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 F. This is lone pair. Seesaw means these are the two threads and one student can sit here, one child can sit over there. So this is the seesaw shape. SO4 has got seesaw shape. Next we have CLF3. 7 plus 1 plus 1 plus 1. So 10 electrons. Means 5 pairs. 5 pairs. 5 pairs will be taken in what way? 5 pairs will be taken in a TBP fashion, the arrangement of electron pairs. But there is only 3 bonds and 2 lone pairs are there. 3 bond pairs and 2 lone pairs. 2 lone pairs are kept at the equatorial position. 2 lone pairs are kept at the equatorial position. So this is a T shape. So this is T shape. Here there is a lone pair and then here also there is a lone pair. One up, one down, one up, one down, So this is T shape, and here there is a lone pair. Here there is a lone pair and one lone pair here also. Like this. T shape. T shape in this sense. T shape. Don't look at the lone pair for the shape. Next, ClF5. 7 electrons, valence electrons from chlorine and 1 electron. So 12 electrons means 6 pairs. 12 electrons means 6 pairs. 6 pairs can be arranged in what way? In an octahedral. Octahedral. This is that octahedral. Here on this plane 4, 1 up, 1 down. This is octahedral. But here one pair is lone pair. Only so I am removing this. I am removing this, and I am fitting this. Okay, so down one is a or upper one, anyone you can take. Down one is a lone pair, right? Down one is a lone pair. I can keep it straight. So down one is a lone pair. I can keep it up also, no problem. So for drawing, like this. Here there is a lone. This is a lone. You can join. So this will be having a square pyramidal shape. 1 up and 4 at the corners of a square. Join from the top to this corners. So you will be getting a square pyramid. So the shape of ClF5 molecule is square pyramid. Next is XCFO. Xc having 8 electrons in a valence shell and 1 from each fluorine. So altogether 12 electrons is below example. And these 12 electrons are to be put in 6 pairs. But you see, only 4 bond pairs, so 2 lone pairs. 4 BPs and 2 NPs. These 4 BPs are kept towards the corners of a square and one above, one below. Anyway, these lone pairs are to be kept far apart so that they should stay apart so that there should be minimum repulsion. Minimum repulsion, for that only they stay far apart. Minimum repulsion which gives maximum stability. So I am replacing this one and I am putting a lone pair on the top. Now look at the structure. Lone pairs, don't look at the lone pairs for the shape because that is not a covalent bond. There is only lone pairs. Only covalent bonds are directional. So this is square planar like this. You see, this is square planar. So don't look at this lone pair for the shape. Only the corners you see. So the shape is that is XCF4. Look at only this F, all the 4 F and then XC. This is square planar, one lone pair above, one lone pair below. The shape is square planar. The shape is square planar. So that's about the structures according to the VSEPR theory. Molecules with no lone pairs on the central atom, molecules with lone pairs on the central atom. Alright, thank you.